Okay, so today we're talking about LeChatier's Principle. Let's start with the definition. LeChatier's Principle states that if an equilibrium system, meaning the reaction has gotten to equilibrium, if it is subjected to some kind of stress, the reaction occurs in a direction as to relieve the stress, meaning it's going to try to undo any changes that were made upon it. All right? Think of it as like a self-correcting teeter-totter. Right? So remember, when a reaction is at equilibrium, then the forward rate and the reverse rate are equal. So if something was done to one, where let's say, so you have a teeter-totter. Okay, so let's say you've got a large man on one end, and you've got two little girls sitting on one end. We could have an equilibrium this way, right? But you know that if one of the girls jumps off, then this balance is going to be disrupted. So LeChatier's principle says that if there's any change that happens, the system is going to self-correct. Okay, and so it can do that a number of ways. So let's talk about the primary ways in which the system will correct itself. So the first type of stress or change, and I know it says stress here. When we say stress, we also mean change, like any kind of change. Okay, so not to personify the reaction, it's not a person, so it doesn't actually feel stress. So any kind of change we make. All right, so adding or removing a species. So in a chemical reaction, let's see the equilibrium. So right here, I've got hydrogen iodide as my reactant. I've got hydrogen and iodine as my product. So when we say add or removing a species, this is akin to changing concentrations. So if we add more HI, if hydrogen iodide is added, the effect of that is going to be that we will now have too much reactant relative to a system that should be at equilibrium. So in order to counteract that, this reaction then is going to prompt consumption. Reaction will shift forward. And when I say proceeds forward, what I really mean is proceeds at a forward rate greater than the reverse rate. Because remember, both reactions are always happening. But for the moment, for the time being, the forward rate is going to be happening at a greater rate than the reverse rate. Okay, that is until equilibrium is reestablished. So reaction rate proceeds forward at a greater rate consuming the extra reactant until the equilibrium ratio is established. I should say reestablished. What equilibrium ratio am I talking of? What value is it that we're trying to get back to? Kc, yeah. Mm-hmm. So, if hydrogen was, oh my goodness, I'm sorry. Hold on a second. We got to edit this. Hydrogen is a product. Hydrogen is a product. That's my bad. Let's back up the truck. Let's change that. the other way, it proceeds backwards. What was I reading? It proceeds backwards at a greater rate, consuming the excess, that's product, until the equilibrium is reestablished. Okay, sorry about that. So, if hydrogen is added, the reaction rate goes backward. Now, what is the result of this reaction going backwards? We are going to see an increase in the concentration of HI, right? The H2 will start to come back down to a ratio that's relative to the HI that's appropriate. What happens to the concentration of I2 if this reaction is shifting to the left? It must go down, because in order for this reaction to shift left, to make more product, that because it's trying to consume the excess product, a reverse reaction implies the consumption of iodine. So the iodine concentration must go down as a result. Okay? All right. If hydrogen is removed, the opposite occurs, right? It's going to replace, and this is an important point, right? A reaction will replace anything that is removed. If we are removing hydrogen, hydrogen is a product, that's going to prompt the system to move forward to make more hydrogen, because in order for equilibrium to exist, there must be hydrogen. So it's going to shift forward. The result of this shifting forward then will increase iodine, but it will decrease HI. Right? So this concept of adding or removing anything, you always have to think about, if anything's added, if anything's removed, the reaction is going to shift, right? The equilibrium, by definition, the equilibrium is a balance of a specific ratio of product over reactant. And that balance will be reattained. It will be. You just got to figure out which way it's going to go to do that, and what's the effects on all the other species. Okay? So, either by changing the concentration, meaning increased concentration, decreasing the concentration. All right, now there's more than one way to change concentration. Right? We can add something, we can remove something, but we can also change the volume. Right? If it's a gas, you can change the concentration by changing the volume. Let's talk a little bit about volume. So changing the volume or changing the pressure, first of all, we add this caveat right at the beginning. This applies to gaseous equilibrium, to gases, because you're not really going to change the volume or pressure. There's not going to be any effect if this is an aqueous equilibrium system. Okay, so only to gases. So check your states. Okay, we have 3 case studies here, so let's talk about each one of these individually. So the first one, I have an equilibrium system. It's a decomposition of dinitrogen tetroxide. So it breaks down and it forms nitrogen dioxide gas. Okay. So if we were to increase the volume, right? It says volume change. So increase the volume. By increasing the volume, you are now giving the reaction more space. Let me draw a picture here. Okay, so volume increased. Whenever you increase the volume, you are now, that ratio of product to reactant, right, the K value must be maintained. And so if that value must be maintained, then the system's going to respond in a way to kind of try to make that happen again. Now, the result of increasing volume is that you have more space. So more space means you need more reactants and products to fill that space, but the coefficient of your reactants and products is not the same. So when you increase the volume, the reaction favors the side that can fill the extra space. And the side that can fill the extra space is the side that has a greater coefficient, the most moles. All right, so this reaction shifts right since the product side has more moles than the reactant side. Yeah, Rowan.
So, hypothetically, I don't know if this will happen, but suppose the NO2 was aqueous, would it shift to the left? The NO2 was aqueous and you increase the volume?
Yes.
Okay.
Yes.
So it's the more moles of what? Gas?
Gas. More moles of gas. All right, to test our understanding, let's consider the opposite scenario. Right, so if we were to decrease the volume, right, for this reaction, if we decrease this reaction, we're squeezing it, right? Decreasing the volume of a gaseous system means you're squeezing it. And if you're squeezing it, then the gas cannot exist in a smaller space at the current ratio. So that means the reaction is going to favor the side that doesn't need as much space, and that would be the side with fewer moles. So volume decreased, less space available. Reaction favors side that requires less space. It's going to shift to the left because the reactant side does not need as much space as the products do. Okay. So by using this logic, we apply this to the others. Let's look at the second reaction. So here we have nitrogen reacting with hydrogen. We're forming ammonia. Now, everything is gaseous, so we take account of the moles. We have 4 moles of reactants in gas form. We have 2 moles of products in gas form. So the first change said to increase the volume. By increasing the volume of this system, the system has to fill this extra space. It's going to favor the reverse reaction because there's more moles of gas in the reverse reaction. It's going to shift backwards. We use the term shift backwards or shift left when we're talking about how LeChatier's principle applies. If we decrease this, right? If we decrease this, the volume of this system, the product side is going to be favored, and it's going to shift forward. Now, the application of LeChatier's principle is for us to manipulate how the reaction takes place so that we can benefit from it. So this reaction right here is known as the Haber process, right? And the formation of ammonia was extremely important in times of warfare, because with ammonia, that would allow them to build or to make explosives and dynamite, and that was used to blow up bridges to prevent enemy advance. So there was an embargo on Germany back in World War I where we wouldn't allow them we wouldn't allow goods to be, we prevented them from importing goods because they were World War II. So they learned, the Fritz Haber developed this reaction so that Germany could produce its own ammonia, so that it could build its own explosives, so that it could kind of go on its warpath and do the crazy stuff that it did, right? So, anyways, if I wanted to increase the production of ammonia, then what I learned from that is that I could increase the pressure on the system that would drive the reaction forward, that would increase the ammonia yield. Do you guys see that? We manipulate reactions to do what we want them to do. If we want to make more product, we want to shift this reaction forward, and that will increase the efficiency. Okay? All right. And the third example, the decomposition of hydrogen iodide forms hydrogen and iodine. It's equimolar, right? The reactant side and the product side have the same number of moles. So because they're equimolar, then by changing the pressure, changing the volume, there is no effect. It doesn't favor the reactant side or the product side by altering the pressure or volume, right? So nothing would really change about that. Now, I know that this chart here was representing a change in volume, but remember the change in volume and the change in pressure are inversely related, right? Meaning, increase in pressure is the equivalence to a decrease in volume, and vice versa, right? So whatever the problem is prompting you with, you got to be able to interpret that and say, all right, well, the problem says that we're decreasing the pressure. Well, decreasing the pressure is the same thing as increasing the volume. Okay, so just pay attention to that. Okay, so that's what happens when we change the volume or the pressure. Let's talk about temperature. When we were back in kinetics, last unit, I had mentioned that changing temperature was the only way to change a rate constant. Okay, so that's essentially true for equilibrium constants as well. And so here it's important to understand whether your reaction is endothermic or exothermic. All right, so the dinitrogen tetroxide decomposition reaction. A delta H for this is positive. So this is endothermic, right? It's endothermic because of the positive value. What that means is when this reaction takes place, it takes in heat. It requires heat from the environment in order to happen. In that sense, as far as what we're applying to this discussion, heat would then be considered as a reactant. And I find it helpful to actually write the term heat on the reactant side. So now if you understand heat as a reactant, then we can talk about what happens when we change the temperature. So if we increase the temperature, you are increasing the kinetic energy, you are increasing the amount of heat available for this reaction. It's like you're increasing a reactant. It's going to drive the reaction forward and make more product. It's almost an endothermic reaction. Heat is a reactant. If you decrease the temperature, i.e. cool it down, right? So anytime, if we're going to be cooling this reaction down, you are removing heat. And anytime you remove something, in order to get back to equilibrium, the system's going to try to replace what was removed. So this, if you cool it down, it's going to go in reverse to replace the heat that was removed. Then we extend the same logic to an exothermic reaction. Here, the Haber process is an exothermic reaction, right? Negative delta H means heat is released as a product, so, right, heat as a product. So if you were to increase the temperature of this reaction, increasing the temperature, you now have an abundance of heat. Whereas heat is perceived as a product, that's going to inhibit the forward reaction. It's actually going to start driving the reverse reaction. So the reaction is going to shift backwards. So if you want to make a lot of ammonia, high temperatures is a bad thing. right? What you would do then is you would, during this process, industrially, we would cool this reaction chamber down to help us maximize the yield. And then, again, so yeah, decrease the temperature, cooling it down, removing heat drives the reaction forward because the system's going to try to replace the heat. So, because temperatures shift the equation and because Kc is temperature dependent, Kc is affected. So whenever you apply a temperature change, you can expect that the Kc value will change as well. Right? So heat, here's a generic reaction. Right? So in an endothermic reaction, the Kc increases with temperature increase. In an exothermic reaction, increasing the temperature is going to drive this reaction backwards. So Kc will decrease when the temperature increases. Right? And, these statements here is not so much anything that you need to memorize. As long as you can understand and apply the delta H sign, right, where if the sign is positive, heat is reactant. If the sign is negative, heat is a product. And then you can answer this question then if they tell you the temperature increase or decrease, right? So it's more so about logic than it is memorizing. Okay. So simultaneous equilibrium, we dealt with this a little bit when we were talking about equilibrium laws, right? Simultaneous equilibrium is very, very, very common, right? In industrial chemistry, it's guaranteed, it's virtually guaranteed almost that you have simultaneous equilibrium because rarely does a product involve only one equilibrium system. Right? These would be products such as contact lens solution, right? Medicines, cough syrups, anything that you would buy that you would end up putting in your body, right? There's a lot of equilibrium system going on between the chemicals, or even in soda pop, right? And there's lots of acids in soda pop. Granted, they're called weak acids, and they have to be in an equilibrium because if not in equilibrium, the amount of acid in the soda pop would tear your teeth apart. Granted, they kind of still do that anyways, but anyways, I digress. Okay, so let's look at these reactions here. I have system 1, which shows A reacting with B to form C and D. Okay. And then I have system 2, which has D plus E forms F. Okay. What is the effect on A if F is removed? All right. So the way that you address simultaneous equilibria is you assess directly the first thing that is affected. So the first thing that we're doing is removing F. Okay, so if F is removed, reaction 2 will replace it, right? Well, reaction 2 shifts right to replace F. Okay. Everybody agree? Removing F, the system's got to replace it. Okay. If reaction 2 is shifting to the left, that means what's happening to D and E? They have to decrease in order for reaction 2 to proceed, right? So concentration of D decreases. All right. So if the concentration of D decreases in reaction 2. The concentration of reaction D in system 2 is decreasing. D is also common to reaction 1. And so if we look solely at reaction 1 has to replace D because D is suddenly disappearing. It's suddenly vanishing. So reaction 1 shifts right to replace concentration of D. And in doing so, it's going to consume A, which means A's concentration will decrease. And that's really what they're asking for. What is the effect on A? Right? So it's a domino effect. You start with the thing that was directly changed first, and then you see what effect it will have in any kind of subsequent equilibrium. All right? But you have to provide, you have to justify, you have to provide evidence. The evidence here would be walking through it step by step. F is removed, the reaction shifts right. Why? Because it has to replace F, right? If the reaction shifts right, that means D is decreased in reaction 2. That means in reaction 1, D must be replaced, and the reaction 1 shifts to the right, therefore A is decreased. Right? So these explanations, right, it's got to be clear what you're referring to, especially if there's multiple reactions, cite which reaction, because answers like the reaction shifted. What do you mean the reaction? There's 2 reactions, right? You have to be clear. Okay, you got to walk it through in order. Okay, let's look at the next one. So here I have sodium reacting with water, and it's an unbalanced equation. Oops. Sodium's reacting with water. Oh, how did I know that that was unbalanced? You guys remember? Let's brush up on Unit 1. How did I know that was supposed to be a 2 there? It didn't appear unbalanced because there was 1 sodium atom on the left and 1 sodium ion on the right. But what makes there? What's the need to have a 2 there? Yes, redox balancing. Right, your charges have to be balanced too. Okay. So sodium reacts with water, right? Active metals in water produce hydrogen gas and produce hydroxide. Okay. Then, if we take copper ion and we mix it in, the copper precipitates with the hydroxide and forms copper hydroxide precipitate. The color of the copper ion is a translucent blue, right? That's blue. Whereas the copper hydroxide is cloudy, light blue, or chunky, depending on, how you're viewing it. So, what is observed as a piece of sodium is placed into copper solution? Well, again, the sodium reacts and forms hydroxide in reaction 1. Copper ion precipitates with hydroxide in reaction 2. So if the question is asking what is observed, the answer is solution changes from clear blue to cloudy. Visual evidence is important. Understanding what changes are happening visually and explaining which direction equilibrium systems shift. And this is the crux of a lot of our labs this unit, is visual evidence, right, to justify what the reaction is doing, where it's going. All right. Here's another one. So HCl is a strong acid, so the first reaction is not an equilibrium reaction, right? A, because strong acids separate completely, there is no backwards reaction. B, because it's a strong acid, so I guess that's the main reason. Okay. Although I will say, this is not something you've learned yet. We'll talk about this next unit. But the second reaction, reaction 2, this is actually an equilibrium reaction as well. Okay. But if I were to redraw that equilibrium arrow, it would look like this. Okay, that's an equilibrium arrow as well, but why is it asymmetrical? Why is one side more than the other? What does that imply about something, maybe a constant? High or low constant? What do you think? Yeah. Yeah, it's going to be a high constant. Like, look at that. Your forward reaction is definitely way bigger than your reverse reaction, right? That implies a high K value. Okay? And vice versa, right? If you have a K value that's like very, very small, it would be the opposite. The backwards arrow would be bigger. All right, anyways. So we have 3 reactions. The first is not equilibrium, but the second 2 are. Okay? What is observed as HCl is added to that same test tube, the same test tube that we just tested? All right. So what happens? Well, HCl produces H plus, reaction 1. H plus neutralizes hydroxide, reaction 2. Now, if hydroxide is being neutralized, that means the concentration of hydroxide in reaction 2 is being decreased. Right? So then, reaction 3 shifts left to replace concentration of hydroxide. And if reaction 3 is shifting left, do we see a change in visual appearance? What do we see? We see the regular blue color. Yeah, the blue color. Because the copper hydroxide, what color is that? Cloudy, right? In other words, we observe cloudy blue becomes clear. How are we doing, guys? Still with me? Okay. All right. Let's see. Yeah, we could talk about this today. Okay, so that was LeChatier's principle. The system's going to try to get back to equilibrium. Whatever you do is going to get back to equilibrium. Okay. You know what? Actually, here's what I want to do: talk about something before I talk about KP. So, actually, no, I don't. Never mind. I'll save that for next time. Okay. So there's equilibrium constants, right? There's the umbrella of KEQ. KEQ is generic. But more specifically, we have just finished talking about KC. And KC are equilibrium systems that are concentration based, hence the C. Okay? Then there's KP. P is for pressures, when you have pressure values available. So, because it's an equilibrium constant, it is still subject to variance with temperature, right? All equilibrium constants are subject to temperature, right? So let's take a look at our example again. here is our N2O4 forming NO2, right? If we said, all right, let's write the equilibrium constant expression, the law of mass action, right? Products or reactants, it would look like this. Okay? If you had pressure values, you would be solving for Kp instead, and Kp is not written with brackets, it's written with pressure, p values. But if there's a coefficient, you still square it, so the mathematical mechanics of using different equilibrium constants is still the same. We just, using pressures instead of concentrations. So, having said that, what's the Kp expression for the reaction of calcium carbonate, which is a solid, decomposing to form calcium oxide and carbon dioxide? What would the Kp value be for that? N, what do you think? Kp means you can only use what kind of states?
State?
Well, how do I write Kp expression for this?
Product on the top and reactant on the bottom.
Product on top, reactant on bottom, right? However, this is a caveat you need to know when you're writing equilibrium constants, though, right? Can I use all of that? Everything that's here?
No. Oh, just gas.
Just the gases. In this case, that's all the Kp is. It's going to be equivalent to what the pressure of the CO2 is. Right? Because you have to exclude condensed states. You cannot use pressure values for solid states. You can't use pressure values for liquid states. Right? That's the same rule as with all equilibria. Okay? Let's try another one. The reaction in which nitrogen and hydrogen are combined to form ammonia. All right, so nitrogen gas plus hydrogen gas form ammonia, NH3 gas. We got to balance this. There it is, balanced. Everything's a gas. The Kp would be what? Eva, what would my Kp look like in this case? Exactly. Oops. Yep, there it is. That's all Kp is. You're doing the same thing, different symbols, okay? All right. So let's say we have some gas called A, right? If some gas is called A, then pressure of A can be found using this equation, which should look familiar. You follow? It's ideal gas law. PV equals nRT. Rearrange to solve for P. Okay, P is equal to N. P is equal to N times R times T over V. Oh, N over V, you mean molarity? So P is equal to the molarity times RT. Okay, for gases, specifically for gases. All right, so if we understand that, for the reaction, for this reaction, did we write the Kp for that already? No, we didn't. Okay. So for this reaction, Kp would be equal to the P of NO2 squared over the P of N2O4, right? But isn't P of NO2 equal to the concentration of NO2 times RT? I mean, isn't that how we express pressure? So this is substituted in for that. What about the P of N2O4? P of N2O4 would be equal to the concentration of N2O4 times R times T. And that would be substituted in. And the result of substituting that in gives us this. Okay. But this is still a little messy. It's a little bit messy. This can be cleaned up a little bit. And by cleaning this up, meaning we've got RT that can be canceled on the bottom and the square can be canceled on the top, which means we simplify this to Kp is equal to NO2 quantity squared over N2O4 times RT. Everybody understand what I did? I canceled an RT on top and bottom. All right? So, but if Kc is equal to NO2 squared quantity over N2O4, isn't that also here? So if that's what Kc is equal to, doesn't that mean that Kp is equal to Kc times RT? That's a rhetorical question. The answer is yes. I'm kind of like leading you there. All right. So there is a relationship between Kc and Kp. And that relationship, we can use one to find the other if we use this equation. Now, notice that RT is raised to the exponent of delta Ng. Delta Ng stands for change in the number of gas moles. And what that means is the number of moles of product minus the number of moles of reactant. Okay? So it's a variable. It means it changes with every reaction, and you need to learn how you're going to solve for delta Ng so that you can use this equation correctly. And it's really a simple equation, because look, in the reactions we've talked about, moles of product gas minus moles of reactant gas. 2 minus 1. Delta Ng is 1. So that means for this particular reaction, if you're trying to find Kp or Kc, the exponent on the quantity RT would be 1. Look at our second reaction. We've got 2 moles of gas product. We've got 4 moles of gas reactant. Delta Ng, product gas minus reactant gas, is 2 minus 4. Delta Ng is minus 2. So for this reaction, Kp is equal to Kc times quantity RT raised to the negative 2. Right? Or in other words, Kc over quantity RT squared. In our third reaction, we have null effect, right? 2 minus 2, 0. If that happens, that means Kp is equal to Kc, because the RT is raised to the power of 0, which is 1, drops out. In our third example, 1 mole product gas minus 0 moles is 1. So delta Ng is 1. So Kp is equal to Kc times RT to the 1. Just like the first one was. Yeah, Ron.
We use the regular gas constant for this one, right?
Correct. Correct. This is based on gas pressures. We're using the universal gas constant, 0.0821 liters, atmospheres, mole, Kelvin. Right. It's not an energy calculation here. All right. That's as far as this road goes today.